Okay, so thank you for that introduction, Gunnar. And as Gunnar said, my thesis work was done on behalf of Metsä Board in Husum and in collaboration with RISE Processum. And it involved trying to find a new use for green liquor dregs, and in this case, as a filler in geopolymers. Here is the outline of my presentation. I will start to talk about some background information about the residuals from pulping industry and geopolymers. And then I will talk about the experimental part of the thesis work, and then some results and conclusions. Forestry and pulp and paper industry makes up a large part of the Swedish industry, and it is also growing worldwide. In 2018, there was 420 million tons of paper produced and 184 million tons of pulp produced. And as this industry grows, so does also the generation of residuals. It is estimated that the residual generation annually exceeds 1 million tons globally. The residuals generated are mainly the ones listed here. Previously, landfill was the main disposal method for these residuals, but disposal of materials in landfill must be minimized. And in order for that to happen, new demands and markets are needed to be created for these residuals. This also goes in line with the UN Sustainability Development Goals, and in particular goal number 12, which involves a responsible management of resources and responsible consumption and production. Green liquor dregs are generated in the craft process, and it is separated from the green liquor in the clarifying process. The green liquor dregs are separated in the form of a thick slurry. And the solid content of GLD consists mainly of calcium carbonates, magnesium hydroxide, unburned carbon, metal sulfides, and some minerals. And the liquid phase consists of sodium carbonate and sodium hydroxide, which both are accountable for the high pH of GLD. Fly ash is generated when wood bark and other residues are combusted for energy recovery. And fly ash consists mainly of the elements listed here. Lignosulfonate is generated in the sulfite process, and it is separated from the black liquor. Lignosulfonate consists mainly of sulfonated lignin, which means that the lignin has been partially degraded and substituted with sulfonic acid groups. Lignosulfonate has increasingly been used in concrete production since it has water-reducing properties. The construction sector is considered one of the most energy-intensive sectors. Ordinary Portland cement is the most manufactured material in the world, and about 5% of the global carbon dioxide emissions come from the construction sector. One approach to find a less energy-craving substitute to concrete is the manufacture of a so-called geopolymer. A geopolymer is defined as a cementitious material formed when an inorganic material rich in aluminum and silicon reacts with an alkaline activator. Common alkali activators are sodium hydroxide and potassium hydroxide, as well as sodium silicate. Regarding the aluminosilicate sources, they can be divided into 3 classes. The first class consists of industrial byproducts, and fly ash is one example. The second class is natural reactive aluminosilicate powders, and kaolin is one example from this class. Traditionally, kaolin has been used in ceramics, but nowadays it's also used as a functional filler and in paper coating. The third class is activated aluminosilicates, and one example is metakaolin. This is the conventional aluminosilicate source in geopolymer manufacture, and it is also the calcined form of kaolin, which means that it has gone through a calcination process, which renders the aluminosilicate more reactive. GLD has also been studied in geopolymers, and it has been found that when GLD is used as a filler, it can enhance the physical strength of the geopolymers. This also indicates that using GLD in geopolymers is a feasible way of recycling GLD. It is not yet fully understood how the reaction mechanism works in geopolymerization, but it is similar to zeolithization. And a conceptual model has been presented, which is shown here. And the different processes are presented linearly, but they actually occur concurrently. The dissolution and gelation steps are both caused by the high concentration of hydroxide ions. And there are condensation reactions occurring when the polymerization happens. And during this reaction, water is released. And this is the same water that is absorbed in the dissolution step. So water acts as the reaction medium and resides within the pores of the geopolymer gel. In the reorganization step, a 3D aluminosilicate network is formed, and in the polymerization and hardening step, the microporous structure of the hardened geopolymer is determined. The overall goal of this thesis work was to manufacture a geopolymer with fly ash and GLD from the Metsä Board pulp mill in Husum. It was also to evaluate the geopolymer's suitability as a construction material. Here are the raw materials used in the experimental part. Fly ash and kaolin clay were used as aluminosilicate sources. GLD and lignosulfonate were used as fillers. Sodium hydroxide and sodium silicate solution were used as alkaline activators, and sand was used as aggregates. Cement and water were also used. Here is an overview of the experimental procedure. First, the alkaline activator solution was prepared by magnetic stirring, and aluminosilicate source was then added before the mixture was mixed further. Filler and aggregate were then added, and the geopolymer blend was mixed further before it was cast in plastic molds. The geopolymers were then cured at 40 degrees Celsius for 24 hours before they were demolded and cured at ambient conditions until analysis. The plastic molds were manufactured from plastic pipes and were modified during the course of the experiments. After 7 days and 28 days of curing, the uniaxial compressive strength of the geopolymers were tested, and this was done using a universal testing machine. This machine was equipped with a 100 kilonewton load cell, and it was run at a displacement rate of 0.5 millimeters per minute. This yielded a test curve from which the strength could be calculated. The experiments were carried out in 4 different trial rounds. In the first trial round, the amount of GLD added was varied. An important note here is that the weight percentages presented here are in terms of total weights of dry components only. So sand and alkaline chemicals are excluded from this percentage. In the second trial round, the exclusion of kaolin was evaluated, as well as the addition of lignosulfonate. In the third trial round, both kaolin and lignosulfonate were excluded, and wet GLD was added to one of the batches to compare it to the dried and crushed GLD used in all other batches. Water was also added to all of the batches, and in one batch, 58% of cement was added. In the fourth trial round, the quantity of alkaline activator solution was increased for all batches. Also, for one batch, 58% of cement was added. A cement reference was also manufactured for comparison. The geopolymer blends from the first trial round showed a low workability and low flow, and this resulted in cavities forming, as shown in this figure. The cavities were most prominent for batches D0K and D10K, and this is most likely because of a casting methodology difference. When casting the geopolymers of the later batches, the geopolymer molds were banged against the workbench in order to allow the geopolymer blends to fill in the cavities as much as possible. In the second trial round, lignosulfonate was added in an attempt to increase the flow. However, this only resulted in a slight increase in flow and was not sufficient to reduce the cavities forming. In the third trial round, water was added in the same attempt to try to increase the flow. And this was shown to be more successful since the specimens showed a smoother surface and less cavities. However, after a couple of days occurring, some white areas appeared on almost all the specimens, and this is most likely caused by the phenomenon known as efflorescence. Efflorescence is caused by high sodium oxide loading in combination with low alkaline ion complexation into the geopolymer framework. And these alkali ions diffuse with water towards the surface and accumulates at the surface, forming these white areas. The batches of the fourth trial round show the most prominent efflorescence, and this is likely because of the higher amounts of alkali activator solution used for these batches. Regarding the strength, it could be seen that the strength increased when adding GLD to the geopolymer blends. The exception of batch D10K is likely because of the cavities formed. And batch D25K also showed a slight decrease in strength, and this is likely because of the water absorption properties of GLD, resulting in a drier geopolymer blend and higher risk of cavities forming. Both batches D20K and A40K contained 28% of GLD, and since these batches show the highest strength, this proportion of GLD was used in the further experiments. When excluding kaolin from the geopolymer blend, the strength increased slightly, and when adding lignosulfonate, the strength decreased. These results led to the exclusion of both kaolin and lignosulfonate in further experiments. In the third trial round, when adding water, the strength decreased. And this is likely because of the fact that water acts as the reaction medium, and it resides within the pores of the gel, as I mentioned earlier. And when more water is used, more pores are formed, and a more porous geopolymer has a lower strength. In the fourth trial round, when adding more alkaline activator solution, the strength also decreased, and this is also likely because of the higher liquid content. For all batches, it can be seen that the strength increased over time. Looking at the results from a construction perspective, it can be seen that the strength of the geopolymers were low overall. And comparing it to the cement mortar reference, it can be seen that the strongest geopolymers still had a long way to go. Most formulation modifications resulted in a decrease in strength, and this indicates that more modifications are needed in order to find a stronger geopolymer. One reason for the low strength could be that kaolin was used instead of metakaolin. It has been shown that undehydroxylated clays are less reactive, and since kaolin is the undehydroxylated version of metakaolin, this could be a reason for the low strength. Furthermore, it was found that the fly ash contained low amounts of aluminum and silicon, and since these are the key elements in the geopolymerization reaction, this indicates that the amount of fly ash added was too low, and more fly ash might be needed in the geopolymer blends. Another reason for the low strength could be the efflorescence. it has been shown that efflorescence causes microstructural damage to the geopolymers, which affects the physical strength. To conclude, fly ash-based geopolymers with green liquor dregs were successfully manufactured, and the strongest geopolymer showed a strength of 2.3 megapascals after 28 days of curing, and this contained 28% of GLD. High contents of water and alkali resulted in efflorescence, and the flow and workability increased most efficiently when adding more liquid to the geopolymer blend. However, the higher liquid content also led to a lower strength of the geopolymers. The strength was low overall, and it is of interest to alter the fly ash proportion and using metakaolin to try to increase the strength. Thank you.
Thank you. Interesting work.